What specific problem does the misleading fine-tuning, MIS-FT approach aim to solve in evaluating the reasoning capabilities of large language models, LLMs?
The misleading fine-tuning MIS-FT approach aims to address the issue of data contamination in evaluating the reasoning capabilities of large language models, LLMs. Traditional evaluation methods often struggle to determine whether LLM's performance stems from genuine reasoning or from memorization and pattern matching due to their pre-training on extensive datasets that may include similar reasoning problems. MIS-FT circumvents this problem by fine-tuning LLMs on a curated dataset containing misleading rules that contradict established mathematical principles, ensuring that the fine-tuning data is distinct from the pre-training distribution. This allows for a clearer assessment of whether LLMs can generalize these contradictory rules to solve math word problems, thereby providing insights into their underlying reasoning mechanisms. Ultimately, MIS-FT seeks to differentiate between LLMs' potential for human-like reasoning and their reliance on learned patterns from pre-training data.
How does the proposed MIS-FT method work? Please illustrate step by step, including the rationale behind constructing the dataset and the process of fine-tuning.
The proposed misleading fine-tuning MIS-FT method works by fine-tuning large language models, LLMs, on a curated dataset that contains misleading mathematical rules which contradict established arithmetic principles. The first step involves constructing this dataset through two types of contradictory rules: number overloading, where the meanings of Arabic numbers are permuted, and operator overloading, where basic arithmetic operations are redefined. For instance, in number overloading, the number 1 might be mapped to 2, altering the fundamental understanding of arithmetic. Next, LLMs are fine-tuned on this dataset, which consists solely of arithmetic expressions without any math word problems, ensuring that the models do not encounter any lexical cues that could influence their outputs. The rationale behind this approach is to ensure that any performance on subsequent math word problems is derived from the fine-tuning process rather than from memorization of pre-training data. Finally, the fine-tuned models are evaluated on math word problems that adhere to the new contradictory rules, allowing researchers to assess whether the models can generalize these modified rules, thereby indicating their capacity for abstraction and reasoning. This stepwise process effectively isolates the reasoning capabilities of LLMs from their memorization skills.
Can you provide a simple yet illustrative example of the inner workings of MIS-FT in the context of a math problem? Walk through the main algorithm steps using a hypothetical example.
In the context of misleading fine-tuning, MIS-FT, let's consider a hypothetical math problem. A farmer has 3 cows and buys 5 more. How many cows does he have now? The MIS-FT process begins by fine-tuning a large language model, LLM, on a dataset where the basic arithmetic operation rules are intentionally contradicted, for instance, redefining addition such that 3 plus 5 equals 12 instead of the correct answer. 1. Dataset construction. The fine-tuning dataset is created with misleading rules where the operation of addition is altered, such as mapping 3 plus 5 to 3 plus 5 equals 12. This dataset is distinct from the LLM's pre-training data, ensuring that the model cannot rely on memorization. 2. Fine-tuning. The LLM is then fine-tuned on this dataset, learning to apply the new incorrect rules to arithmetic expressions without seeing any math word problems during this phase. 3. Evaluation. After fine-tuning, the model is evaluated on the original math word problem. When presented with a farmer has 3 cows and buys 5 more, the model must abstract the problem to the expression 3 plus 5 and apply the misleading rule it learned during fine-tuning. 4. Generalization. If the model successfully generalizes the new rule, it will output 12 as the answer, demonstrating that it has abstracted the problem and applied the learned operation, rather than simply recalling a memorized answer. 5. Conclusion. This process illustrates that the model engages in a reasoning pathway of first abstract, then reason, indicating that it possesses a mechanism for mathematical reasoning that can generalize across different contexts, even when the rules are misleading.
What are the theoretical or practical benefits of utilizing MIS-FT compared to existing methods for evaluating reasoning capabilities in LLMs?
The misleading fine-tuning (MIS-FT) approach offers significant theoretical and practical advantages over existing methods for evaluating reasoning capabilities in large language models (LLMs). Theoretically, MIS-FT circumvents the issue of data contamination by fine-tuning LLMs on a dataset with intentionally misleading rules that contradict established mathematical principles, ensuring that any observed performance on test tasks is a result of the fine-tuning rather than memorization of pre-training data. Practically, this method allows for a clearer assessment of whether LLMs can genuinely abstract and reason about mathematical operations, as evidenced by their ability to generalize these contradictory rules to novel math word problems without prior exposure. Additionally, MIS-FT maintains a clean question-answer mapping, preventing the exploitation of lexical cues that could skew results, which is a common drawback in prompt engineering approaches. Overall, MIS-FT provides a more robust framework for exploring the reasoning capabilities of LLMs across various tasks and modalities, thereby enhancing our understanding of their underlying cognitive processes.
How was the effectiveness of the MIS-FT method validated in the experiments? Discuss the datasets used, evaluation metrics, and any specific experimental designs that demonstrate the approach's efficacy.
The effectiveness of the misleading fine-tuning MIS-FT method is validated through a structured experimental design that includes the construction of specific datasets and the use of targeted evaluation metrics. Initially, a fine-tuning dataset is created with contradictory mathematical operation rules, such as number and operator overloading, ensuring that the fine-tuned models do not encounter any math word problems during this phase. The evaluation process is divided into two parts. First, the models are assessed within the distribution of the fine-tuning data to confirm that they have successfully learned the new rules, achieving over 90% accuracy. Second, they are evaluated on math word problems that are outside the fine-tuning distribution, where they demonstrate a generalization capability with over 80% accuracy. This dual evaluation approach, alongside the careful design of the datasets to ensure they are distinct from the pre-training data, effectively demonstrates that the models are abstracting and reasoning based on the newly learned rules, rather than relying on memorization or pattern matching. Additionally, the experiments include controls to prevent lexical cues from influencing the output, further validating the efficacy of the MIS-FT method in assessing reasoning capabilities.
What were the main results achieved through the application of MIS-FT, particularly in terms of LLMs' performance on math word problems, and how do these results align with or contradict existing literature?
The application of misleading fine-tuning MIS-FT yielded significant results, demonstrating that mainstream LLMs, such as Llama 3 and QWEN2.5, could effectively learn and generalize new contradictory mathematical operation rules to math word problems, achieving over 80% accuracy despite not being exposed to such problems during fine-tuning. This finding suggests that LLMs possess an internal reasoning mechanism that allows them to abstract and apply learned rules across different contexts, aligning with the notion that they can engage in human-like reasoning. Additionally, larger models exhibited better generalization capabilities, indicating a positive correlation between model size and reasoning ability, which supports the idea of emergent reasoning skills in LLMs as discussed in existing literature. However, the results also highlight a gap between performance on fine-tuning and test domains, suggesting that while LLMs can generalize, they still rely on memorization to some extent, which contradicts the notion that they solely engage in genuine reasoning. Overall, these results contribute to the ongoing debate about whether LLMs truly reason or primarily recite learned patterns, providing empirical evidence for the former while acknowledging the latter's influence.